It usually happens in the dead of winter. You wake up, the house is just freezing, and you stumble into your bathroom, bracing yourself for that icy shock of the tile floor.
Oh, yeah. The worst.
Right. But instead, you step down, and it's perfectly, wonderfully warm, and it feels like magic. But
Hmm.
the reality is, beneath your feet is this landscape of cold, hard, incredibly precise math.
Yeah, exactly. And we were talking about an environment where a calculation being off by just a few centimeters can mean the difference between, a comfortably warm room and a completely destroyed floor.
Totally. So today, we are cracking open the actual engineering blueprints for this deep dive. We're looking at highly technical Danfoss and DEVI user guides detailing exact material limits all the way up to the schematics used in massive professional sports stadiums. We really want to find out exactly how this invisible heat works.
Right. Because the mission here is to decode the exact science of indoor and outdoor floor heating. We're taking what seems like a totally mundane architectural luxury and exploring the thermal dynamics, the material science, and honestly, the high-level risk management behind it.
Because you walk on these surfaces every single day. But have you ever considered the meticulous mathematical layers required to keep your feet warm without, warping your hardwood, melting your carpet, or putting a multi-million-dollar sports game in jeopardy?
I mean, most people haven't. They just turn the thermostat dial on the wall and just expect the heat to rise up through the floorboards, but before a single wire is ever laid down.
Or a drop of concrete is poured.
Exactly. Before any of that, you have to establish the fundamental philosophy of the room. Like, what are you actually trying to achieve with this heat? Because the manual makes a very strict, definitive distinction right off the bat. You're forced to choose between a comfort floor heating system and a total or direct floor heating system.
Okay, let's unpack this. Because they sound similar, but the engineering approach is entirely different.
Well, completely different.
Right.
So comfort heating, as the guide defines it, is just the warm floor system. Its only job is to provide a heated surface for your bare feet. You're still relying on radiators or a forced air system to actually heat the air in the room.
Right, it's just tactile.
Yeah. But total floor heating, that is engineered to be the only heat source in the room. It has to combat the room's specific heat loss completely on its own. So if I were to visualize this, comfort heating is like putting a pair of incredibly cozy thermal socks on the room. It just feels nice.
I like that.
But total heating is like turning the floor itself into the entire house's furnace. I mean, it has to do all the heavy lifting.
Exactly. The priority shifts completely from just that tactile experience to aggressive climate control. And the way you engineer the difference between those two philosophies, it comes down to a very specific metric, and that's the cable-to-cable
The
distance.
spacing. Yeah, the spacing. The manual spends a tremendous amount of time breaking down how tightly you pack the heating elements together under the floor, using these step systems like DVI Fast or DV Clip.
See, I'm looking at the numbers on this spacing, and my brain just immediately assumes tighter cables just mean the floor gets hot faster. Is that wrong? Like, does a 5 centimeter spacing just mean you don't have to wait as long for your toes to warm up?
Well, it's less about a race to get warm and more about the total volume of thermal energy being injected into the physical mass of the floor. Because heat radiates outward from these cables in like a cylindrical wave.
Okay.
So if you place the cables far apart, say 25 centimeters, those waves of heat barely overlap by the time they reach the surface of your floor. You end up with an output dropping to a pretty mild 24 to 40 watts per square meter, depending on the cable.
Which is perfect for just taking the chill off the tile.
Right. But if you pack them a tight 5 centimeters apart, those heat waves overlap intensely and immediately. You are generating a blazing 200 watts per square meter. It creates this solid, impenetrable blanket of thermal energy pushing upward.
To overwhelm the cold air pressing into the room from the outside windows?
Exactly.
So if you space them too far apart in a room that needs total heating, you don't just get a cold room, you might actually feel like zebra stripes of hot and cold under your feet because the thermal waves aren't overlapping properly.
Yes, which is an incredibly uncomfortable feeling. And there was a fascinating electrical technicality the manual points out regarding that massive energy injection.
Oh, the voltage thing?
Yeah. All of these outputs, the 200 watts, the 40 watts, they're mathematically calculated assuming a perfectly standard 230-volt power supply.
Wait, really? But a lot of older homes or just homes in different regional grids, they run closer to 220 volt.
They do. And if your house operates on a 220-volt grid, the guide explicitly notes that the output must be recalculated using a precise coefficient of 0.91.
So you're losing almost 10% of your heating power just because of a slight basically unnoticeable variance in your home's electrical grid.
Yeah.
I mean, if you engineered a total heating system right on the very edge of the room's heat loss requirements, meaning you calculated exactly enough heat to beat the winter air, and you didn't account for that 0.91 coefficient, your room would literally never get fully warm on a freezing day.
It wouldn't. It really highlights how this isn't just a basic construction task where you just lay down some wire.
Hmm.
It's a rigid electrical engineering equation. You're balancing grid voltage, cable resistance, spatial geometry, and thermal dynamics before the floor even exists.
Here's where it gets really interesting, though, because once you've defined your goal and you've done that math, you have to look at the physical environment itself. The guide rigidly divides the world of floors into two distinct battlegrounds.
The wet and dry installations.
Yes, wet installations and dry installations. And the rules for these two environments are entirely different ecosystems.
Right. So a wet installation is where your heating cables or mats are embedded directly into a liquid that will cure.
Like tile glue or screed or a thick layer of concrete.
Exactly. Whereas a dry installation is where the heating elements are sitting under materials that don't require any liquid binding. So wooden joists, linoleum, parquet, or heavy carpets.
And the wattage limits they enforce here completely threw me at first. I mean, for a wet system one buried deep in concrete or sitting under heavy marble tiles, the guide allows for massive power outputs. You can push it all the way up to that maximum 200 watts per square meter using heavy-duty products like the DEVI Mat 200T or the DEVI Heat 150S.
Right.
But for a dry system, if you are putting this under a beautiful wooden floor or a thick carpet, you are strictly capped at 100 watts per square meter. And if you're installing it suspended between wooden joists, it drops even further to a strict maximum of 80 watts per square meter.
And that restriction isn't a recommendation, by the way. It is an absolute mandate.
But see, this is what surprised me. Wood and carpet are classic insulators. They're thick, they hold temperature. My initial thought was, shouldn't thick, insulating materials require more power to push the heat all the way through to your feet? Why are they capping the power so drastically on the exact materials that are hardest to heat through?
What's fascinating here is that you've just identified the exact danger, but you're actually looking at it in reverse.
Oh, really?
Yeah, you are absolutely right that wood and carpet are excellent insulators. But an insulator doesn't just stop cold from coming up. Its primary function is stopping heat from getting out.
Ah.
Concrete, stone, and tile, they're thermal masses. They act like giant sponges for heat. They absorb that 200 watts of thermal energy and rapidly radiate it away into the room, dissipating the energy safely.
Oh, wow. Okay. So the heat has an immediate escape route in a wet system. It just flows right through the rock.
Exactly. But wood acts like a thermal blanket. It traps the heat. If you pump 200 watts per square meter directly under a wooden floor, that energy has nowhere to go. It builds up rapidly inside the subfloor.
Oh, I see.
Yeah, so you wouldn't just be warming your toes. You would be baking the wood from the inside out. You risk severely warping the expensive floorboards, degrading the chemical adhesives holding the room together, and ultimately creating a very real, severe fire hazard inside your home.
That makes so much sense. It's like putting a heavy winter parka over a glowing space heater. The coat isn't going to help warm the room. It's just going to trap the heat until it literally catches on fire.
Precisely.
You would essentially be turning your living room into a slow cooker. So because of these intense material limits and the danger of trapped heat, the actual installation process isn't just about throwing some wires on the plywood and hoping the house doesn't bake.
No, not at all. It requires a meticulously engineered architectural sandwich. The manual outlines incredibly specific layer setups to ensure the heat moves exactly where it needs to go while protecting all the materials around it.
Let's break one of these down because the hidden complexity is staggering. Let's say you're putting down a beautiful parquet floor over a concrete subfloor on the ground level of a house. Okay.
The guide shows a cross-section of what's actually happening beneath your feet, and it's wild. You start with the concrete subfloor. Then you lay down a dedicated insulation layer.
Which is a crucial first step. Because if you skip the insulation layer on a ground floor, the thermal energy will just follow the path of least resistance.
Right.
Instead of pushing up through the wood, it will push down into the earth. You would literally be paying your utility bill to heat the dirt beneath your foundation.
Right. Nobody wants to do that. So you block the heat from going down. Then on top of that insulation, you lay down a vapor barrier or a damp-proof membrane.
Yeah, to prevent ground moisture from rising up.
Exactly. To protect the electronics and keep the wood from rotting. Over that vapor barrier, you install these specialized device all metal plates with pre-cut grooves. Then you carefully weave the actual heating cable, like a DV Flex 6T or 10T, through those grooves to ensure the spacing is mathematically perfect.
Yep, the spacing again. Right. Then you add a noise absorption layer so the floor doesn't echo. And then finally, the parquet floor goes on top. I mean, it's a 7-layer cake of thermal and moisture management.
It really is. And nested deep within that complex sandwich is perhaps the most important piece of the entire system. Honestly, it's the unsung hero of thermal engineering,
The floor sensor.
the floor sensor. Because all this heat generation needs a brain to tell it when the floor has reached its maximum safe temperature.
Yes. But the guide is very, very specific about how this sensor is installed. It absolutely mandates that the floor sensor must be installed inside a specialized, heavy-duty plastic conduit pipe.
Right, they specifically mentioned the flex pipe or the Astroflex.
Yeah, usually about the thickness of a standard pencil.
Yeah,
And that runs from the wall thermostat all the way down into the floor. It cannot just be buried directly in the cement or the tile glue like the heating cables themselves. It must be inside that smooth plastic tube.
and the reason for that is purely about protecting the homeowner's sanity and wallet in the future. Because the heating cables themselves are incredibly durable. They're designed to sit entombed in concrete for decades. But the floor sensor,
It's just a little electronic part.
exactly, it's a highly sensitive, relatively inexpensive electronic component. And like all electronics, sensors can eventually fail.
So what does this all mean for the layout? I was thinking about this, and that plastic tube is essentially a tech escape tunnel.
A tech escape tunnel, I love that.
Right, because if you bury a 10-cent sensor directly in the wet concrete and it breaks 5 years later, your entire heating system is completely blind. It won't know if the floor is 50 degrees or 150 degrees, so it shuts down entirely for safety. And without that plastic conduit pipe, replacing that sensor would be an absolute nightmare.
You would have to locate the exact spot the sensor was buried, take a jackhammer to your beautiful, newly installed marble bathroom floor, and basically chisel out the concrete just to replace a wire the size of a matchstick.
But by sealing it in that smooth plastic pipe, if the sensor dies, you just walk up to the thermostat on the wall, pull the dead sensor wire up out of the wall like a long piece of spaghetti, and then just slide a brand new wire down the tube until it hits the end under the floor.
It's a brilliant piece of invisible foresight.
Truly.
And, speaking of foresight, the guide also outlines strict safety mandates regarding the visibility of the entire system. Because this infrastructure is totally hidden once the floor is laid, the manual requires that the presence of this high-voltage layer must be made evident by bright caution signs in the fuse box.
Oh, and explicit markings along the circuit line, too.
Yes.
Because the next person who buys the house 10 years from now won't have any idea there is a massive electrical grid sitting right under their feet.
Imagine a plumber coming in to install a new vanity or drill a hole for a drain pipe. If they don't know they're standing on top of a live electrical network, a simple drill bit could cause a catastrophic short circuit or a severe injury.
Right.
So the electrical documentation has to explicitly state the system is there. It's really about protecting the building and the future occupants from the invisible power running right beneath them.
So we've seen how this technology protects a home's wooden floors. We've seen how a simple plastic tube future-proofs bathroom tiles. But what happens when the stakes are higher than a warped floorboard in a living room?
Oh, we're scaling up.
We're scaling up. What happens when you apply this exact same math to a multi-million-dollar NFL game in the middle of a blizzard?
Well, this is where we transition to the massive sports field heating systems outlined in the summary document. And at this scale, the conversation entirely abandons the concept of barefoot comfort.
Yeah, nobody is walking out there in bare feet.
Right. We are no longer talking about keeping your toes warm after a morning shower. The goal shifts strictly and completely to high-level risk reduction.
I want everyone listening to actively imagine the sheer scale of the wattage required here. We were just talking about how a small residential bathroom might use, what, a DEVI 150T, a few hundred watts total to keep a small room comfortable.
Yeah.
What is the sheer electrical load required to melt a blizzard off a multi-acre professional soccer pitch? I mean, we are talking about megawatts of power networked in endless rows under the turf, fighting aggressively against the open winter atmosphere.
It's massive. And if we connect this to the bigger picture, you start to see how thermal engineering transitions from a residential luxury into a critical financial and safety instrument. For major sports leagues, a frozen field isn't just an inconvenience, it is a massive dual threat.
Financial and physical.
Exactly.
Yeah.
First, you have the immense financial risks.
Hmm.
If a professional game is postponed because the field is an unplayable sheet of ice, the league loses millions of dollars in broadcasting rights, ticket sales, concession revenue, and it creates a total logistical nightmare for scheduling.
So the heat beneath the grass is literally an insurance policy for the primetime broadcast schedule. It basically guarantees the product can be delivered to millions of viewers, regardless of what the winter weather is doing.
The show goes on, period.
Mm-hmm.
But the second threat is even more critical than the broadcast revenue, and that's the physical risk to the athletes on the field.
Yeah, falling on frozen soil isn't like falling on grass. It's like falling on green-painted concrete.
Exactly. A frozen, unyielding surface drastically increases the rate of severe player injuries. We're talking about torn ligaments, major concussions, fractures. The biomechanics of sports literally rely on the ground having a certain amount of give.
Right.
So the sports field heating system works dynamically with outdoor sensors to keep the soil at a precise, malleable temperature. It ensures the player's cleats can actually penetrate and grip the earth to make sharp turns without snapping an ankle.
Wow.
So the exact same principle that prevents your hardwood floor from warping is being used to protect a $100 million athlete's knees from shattering on impact.
It is the exact same math. The same grid voltage calculations, the same cable-to-cable overlapping heat waves, the same sensors sitting in escape tunnels, just scaled up to a monstrous stadium-sized degree.
It really is.
It really makes you appreciate the engineering journey we've taken today. You know, we started at the micro level, looking at the precise 80 watts per square meter cap required to keep from baking a wooden floor into a fire hazard.
And we followed those identical principles all the way up to the macro application, where underground heating cables are actively managing the financial stability of global sports franchises and the physical safety of professional athletes.
It's incredible how adaptable this underlying technology is.
This raises an important question, really. It encourages us to look down at our own floors. Whether we're standing in a kitchen, a bathroom, or even looking out over a local sports field, and just appreciate the silent, invisible infrastructure below us.
Absolutely.
There are vast networks of calculated thermal dynamics actively working below the surface to keep our environment safe, balanced, and functional.
It really changes how you look at the ground. And actually, that leaves me with an entirely new application to ponder, something that builds on everything we've just discussed.
Oh, what's that?
Well, if we can precisely control the thermal environment under our floors, and we can pump megawatts of power under massive sports fields to prevent freezing and physical injury, what if we applied this globally to outdoor civic infrastructure?
Oh, wow.
Right. Imagine a future where smart, electrically heated roads and sidewalks are the standard. I mean, if we can melt a blizzard off a soccer pitch, we can melt it off a busy downtown intersection. Imagine a winter city that entirely eliminates the need for snowplows.
That would be wild.
Imagine eliminating the thousands of winter car crashes caused by invisible black ice. Imagine never having to use environmentally damaging road salt ever again because the asphalt itself just gently evaporates the snow as it falls. How would applying this invisible heat fundamentally reshape the way we build and live in our winter cities?
That's an amazing thought.
Because the math is already there. The cables are already there. It's really just a matter of scale. Just something to think about the next time you step onto a perfectly warm tile floor on a freezing morning.